All right, so we're in week 5. We've done 4 weeks learning all about transformers, and in theory, we've got a model that we like and we'd like to deploy now. So this whole session today will just be discussing all of the things that you might consider when you're actually deploying a model. So we'll cover all of this stuff. You've got a model you like, how would you deploy it? And then I'll be talking a lot about the various techniques to speed it up, do inference efficiently, and just get the most bang for your buck on all of these different fronts. So the first thing that I want to start off with is talking about 2 different kind of modes of inference. And I want to shout out a little bit of vocab right at the beginning too. So you might hear inference, you might say scoring, you might hear prediction. People use these interchangeably. It kind of depends on the domain that they came from and what background that they have. So just know I tend to say inference, but you might hear people say those other things, and just know that they're typically the same. So the first thing that I wanted to really talk about is online versus batch prediction. So online, the way that I typically think of it is like you have some API or something, and it's going to get individual samples passed to it. And so someone uses your app, they hit the certain button, and then it sends the data to your model, and then it expects a response back. That's kind of the way that I typically think of that. And that can take various different forms. But that's kind of the simplest one. And so the most important typically parameter on that one is the latency, the amount of time that it takes to get a response back. So someone clicks the button and then it sends the data to your model returns back a prediction, and then that gets displayed on your app somewhere. And it's important that that latency is not huge. Typically, it depends on exactly what the domain is, but someone doesn't want to have their phone app and click a button and then it freezes for 15 seconds or something like that. So the latency in that case is very important. You want to make sure that that's as minimal as you can. And then another one is batch prediction. So online prediction was single sample passed to your model and then returning a prediction back. Batch prediction is more like, imagine that you have some pool of data and you want to apply your prediction or your model to all of that data. So you've got 100,000 rows from new customers from that day, for example, and you want to run some model on top of their data. And so that's what a batch prediction might look like. And so typically someone has a database, and then you say, I want to run on all of the rows or all of the new rows or something like that, and do that every night or every some certain amount of time. It's something where the latency is not actually that important. I got a request to share the notebook. I will copy that in for you guys. Yeah, so that's batch prediction. And in that case, latency probably doesn't matter as much because you're not returning a prediction directly back to someone. You probably care more about throughput. So latency you might measure as like it took 500 milliseconds or 2 seconds to get a prediction back. And whereas throughput, you might measure it as how many records or how much volume can I compute over a certain amount of time, given a certain compute unit. So if I have one GPU system, how much data can I pass through it in a minute or an hour or something like that? And so on a batch job, you might scale up or scale down how many systems you're running based on how much time you actually have to do that work. But ultimately, you want to be able to do as much work in as little time as possible. And so I wanted to call out a couple interesting sites and books that I think are interesting if you want to read more about this stuff. So this is someone that I follow on Twitter, and they have a lot of really good blogs on all kinds of machine learning operation stuff. And so they go in great depth about all kinds of different topics. So if you want to dig very deep in this stuff, there's all the blogs, and then there's also the corresponding book. And so this book gives you a whole bunch of information on the different design patterns and how you might deploy these things and how to most efficiently do various different things. So I'll be giving kind of the spark notes of a lot of these concepts, but if you want to dig very deeply, see more examples of code and all of that stuff, I highly recommend those blog posts and those books. So just wanted to give a shout out to that. So that was kind of the modes of inference. And then now we could do inference just with a PyTorch model. So we take what we already showed in previous weeks. We just say, okay, load up my PyTorch model and then pass new data to it and do predictions with your existing PyTorch. And that will work perfectly fine most of the time. But if you want higher optimized solutions, there's various things out there. And so I would say that my first step, what I would recommend most people do, is the export to Onyx. And so Onyx is this sort of agnostic format that can take in graphs from any number of different libraries. So if you have PyTorch, if you have TensorFlow, if you have scikit-learn, if you have Paddle, if you have models from anywhere, you can export them to Onyx. All of them have built-in Onyx support. And so you export it to Onyx, and then now you have this model object that you can plug into a whole bunch of different runtimes, and then you don't have to bring along the whole PyTorch or TensorFlow or whatever else. It's much more lightweight, and you can do a bunch of cool things with these Onyx models. So here's some example of exporting from a PyTorch model. So I won't go through this in complete detail because it's showing a whole bunch of PyTorch code, but kind of the key point here is back in my notebook. Basically, the process to export this to Onyx from PyTorch, which is what we've been using this whole time, is as simple as building your model. Now you have your model available here, and then you give it to this export function. So torch.onyx.export, you give it your model, and then you have to give it some example input. And so this actually doesn't have to be anything real. You can just basically say, give it something in the right shape, the right format of data to pass to it. So like in this example they showed, you just give it a certain batch size, one channel, certain height, certain width, and then you pass it to the model. And what it's doing here is it's basically running the model and saying, what operations am I doing while I pass all of this data through the model? And then it kind of writes that down, and it can compile it and write the Onyx format out for you. And so you eventually get this output called super resolution.onyx. This is just what they named their model from the documentation. And so that's really the gist of it. It's not very hard. The first time I did it, I thought it was going to be much more complicated, but all you really need to do is say, have your model, give it some dummy input, and then it runs the whole thing, and it just kind of sweeps through your model and figures out what computation do I need to do in order to execute the model correctly in the Onyx format. And I've found that it works out of the box on pretty much everything, as long as you have just like a core model and you don't have a bunch of other Python inside of your model. So that works well. And then you have your Onyx formatted model. And I talked a little bit about why you would want an Onyx model, but to kind of explain the advantages in more detail, now you have this agnostic model that you can plug anywhere. So it doesn't have to have PyTorch or TensorFlow or whatever else. And you can run it on pretty much any hardware that has an Onyx runtime with it. So you can even transfer between languages. So you can build your model in Python, export it to Onyx, and then you don't need PyTorch. You can run it on some other system running C++ or Java or whatever, as long as it has some compatible Onyx runtime. And so there's the Onyx model, which is what you've just exported. And then there's the Onyx runtimes, which is what actually executes the model. And there's all kinds of different options for that. And we'll talk about a few of those as we get further along. And so one of the nice things about Onyx is you can run it on pretty much any platform. So if you want it to run on CPU, GPU, even M1 Max or mobile processors or whatever else, we'll see some of the options there. And so that's what this graphic is showing, is you can take all of these different training frameworks and even more than is shown here, output it to the specific Onyx format, and then load up some Onyx runtime, and then you can execute it on any number of different devices. It's just kind of this agnostic object that can fit anywhere. And the other nice thing with Onyx is because it's kind of this super layer that covers everything else. This is where a lot of people have put the optimization effort. So if you have an Onyx exported model, you can go try various runtimes and figure out which one is fastest. And you can also run various optimization tools on top of it. So you can get an even better optimized graph out of this Onyx model. So here's a list of all of the different options. So if you're interested in CPU, here's a bunch. If you're interested in GPU, here's a bunch of options. This largely depends on which GPU you actually have. So if you have an Intel GPU, you can use OpenVINO. If you have AMD, you can use the ROC M1. If you have NVIDIA, you can use CUDA or TensorRT, and all kinds of different variations. So a really common one is this Qualcomm SNPE. This is what's in everyone's phones. A lot of people have Qualcomm-based processors in their phones. And so in a lot of your cool phone applications, you're probably running Onyx and you don't even realize it, because this Qualcomm SNPE Onyx runtime is very good and runs directly on your phone hardware. So I just thought I'd call it out. So here's how you export the model. And then here's how you load the model. I think that this is pretty neat. You can load it in and then you can check it. And so what this does is it will load in your model and then it will run this checking function just to basically make sure. So you had PyTorch or TensorFlow or whatever else to start with. And then it's assumed that Onyx has all of the different operations that it needs, but that might not be the case. And so this checking function will actually go and make sure we have valid operations for this specific model, all the different layers that you might have. And then it also has valid implementations for the specific hardware that you're on. So this can check and make sure that you might have run this on some AMD system and you want to try it on an Intel system. This checking function will make sure that there's valid operations for your specific hardware. And so this is all of the code to actually do inference. And this is kind of nice because this will be the same no matter what model you plug in here. You don't have to bring along some huge model definition. If you look at what the stuff is under the hood for the various transformer models, you look at it and it's this huge pile of layers that you have to define the whole thing. And luckily we're using HuggingFace and it's kind of hiding a lot of that away from us. But this Onyx runtime stuff makes it very nice in terms of it's just saying, load this file. I don't have to define any of this stuff and then load in weight specifically and make sure everything's correct. You just basically say, I have an Onyx model. It doesn't matter what it is. And you can very easily just plug in 8 different Onyx files and just have them all over the place. And you don't have any extra code. It's just in the weights of the file. And then when you want to do inference, it's as simple as just passing it a NumPy array. So you have your model, you give it your inputs, and then you just pass that into the model, and then it will output something. And so one of the nice things that you can do to verify your results is you can use this function. It's just a basic NumPy function that's just measuring, are my outputs the same as they were before? So you do inference with your you do your inference with TensorFlow or PyTorch or whatever, and then you get those outputs, and then you compare that to your Onyx results, and then you have clarity knowing that the results are the same, its outputs are the same, so that they are lined up. So to Jerry's question there, I don't expect for this to run correctly, actually. So I've pulled in snippets from a bunch of different places, but I don't have true implementation of all of this stuff. So I haven't taken a model all the way through. I'm just showing the snippets from all of the various different tools that you might interact with. So it would take a little bit of customization to actually get them lined up, but it shows the general idea at least. So here's what the inference looks like specifically for transformers. It's pretty simple. You say, load in my model that you saved out as Onyx format, and then do tokenization on whatever you had, output it in NumPy format, and then you just say, run the model, basically. And so it's kind of incredible that you can do so much work in what amounts to basically 4 lines of code, because when you look at this is all of the complex logic of breaking your text into chunks that are correct for your specific model. Here's loading in a huge model definition that can be 100 million plus parameters. And then you're actually doing the tokenization, and then you're running the entire model, and it's 4 lines of code, and you have this whole thing that is very simple to actually run. It's not some complicated process to try and get all of this stuff defined. You don't have to do forward pass and all of these layers and this whole 50 lines of code just to do the tokenization. It's just all abstracted away, so you don't have to do a whole ton of work there. So I think that Onyx is very useful in this regard. So I mentioned we'll be looking at various different runtimes and tools on top of Onyx, and one of these that I found really useful, I don't know how they say it, I assume it's OpenVino, is a tool from Intel. And basically what this does is it will try to recompile your model for whatever specific hardware you're on. So Onyx gives you this kind of agnostic blob, and OpenVino will then take that and try to reformat it specific to your hardware. So if you have an AMD CPU or Intel CPU or Intel graphics card, for example, it will actually do this recompilation step to try to optimize it. So if you have certain newer processor that has some new feature, it will try to do more optimized versions of whatever you're trying to do. And I've had really good luck with this. It's pretty simple to set up, and then it also gives you really good benefits on speed. So in my experiments, I've been working more with OCR systems than I have with transformers, but I've seen as much as 2x speed up over Onyx itself. So the improvement that I've seen is I had a PyTorch model, and then I took PyTorch to Onyx, and from there I saw like a 15 to 30% improvement. And then going from Onyx to OpenVino, I saw a 2 times improvement over that. And so going to OpenVino on CPU ended up being much, much faster than PyTorch because of all of the optimizations that they can put in place specific to your hardware. I also want to mention that it does much better at utilizing your hardware. So if you run it on PyTorch, you might see pretty low utilization. You might not see it hitting all of the cores. You might see it only using like 20% or something like that. And when you do OpenVINO, you'll see that it lights up a whole lot more. So I thought that was kind of interesting and worth calling out. It seems to be doing a better job of utilizing the hardware versus just simplifying the work. So one of the cool things with OpenVINO is it comes along with this deep learning workbench, and there's a million different things that you can do inside of this workbench. I won't show the whole thing, but basically it's a little tool that you can use to plug in your Onyx model. So you take your Onyx model, you upload it here, or you run the tool locally. And then you can do a whole bunch of different optimizations on top of it and check if there's some way to improve it. And it will do a whole bunch of work for you in terms of benchmarking, measuring the latency, measuring the throughput, seeing how resolution affects speed and number of tokens, and a whole bunch of different stuff that's really interesting. So you can plug in your model and then go through this whole process of what ways can I speed up to performance. I don't know if I don't have access to this anymore, but I did play with this a while ago. So we'll talk about some of the optimizations you can do in this deep learning workbench in a later section. But I wanted to talk about some of the other runtimes first. Yeah, I just saw your question, Jerry. We'll talk about those in a second after I talk about the other runtimes. So another one that I wanted to call out, OpenVINO is great for CPUs, and then there's various other things for GPUs. So the one that I typically see brought up is TensorRT, and so this is directly from NVIDIA. They have this runtime that tries to help you do inference extremely fast. So it's the same thing that OpenVINO is to CPUs, TensorRT is to their GPUs. So it's not going to help you on AMD graphics cards or Intel graphics cards or anything else. It's only for NVIDIA, but it's supposed to highly optimize for their specific hardware. And they claim some really, really impressive performance benefits. I've tried it myself and not been able to get good performance. I haven't spent too much time on it. But it's kind of the same thing as OpenVINO, where you say, here's an Onyx model, take it into TensorRT, run some recompilation step for your specific hardware, and then all of a sudden they claim that it's like 8 times faster or something like that. That hasn't personally been my experience. I've actually had times where it's made things much slower. But I think that's down to the specific model that you're using and the specific hardware, and making sure that you have all of the dependencies set up correctly. And so I tried on it for a few hours, couldn't get it to work properly, and just gave up. So you might have better luck than me, but I haven't had great experience with it. Another one that I wanted to mention that's fairly new is this Torch Dynamo tool. And so this is, there's a lot of initiatives on PyTorch to try and improve the speed of these things. And so Torch Dynamo is one of them. And this is sort of a meta tool that tries to optimize things for you in a bunch of different ways. I don't know if I have a better page for this, but basically what it does is it looks at a bunch of the different options and it tries multiple of them, and then it says which one is best for you, and then it can actually save that compiled version for you. So if anyone ever writes a new compiler backend for these models, then it can eventually get integrated into Torch Dynamo, and Torch Dynamo will add that to its slew of options and say, okay, compile it in 8 different ways and see how it performs on all of these different things and then see which one you like, depending on its performance on latency and throughput and all of that stuff that I've talked about before. So Torch Dynamo is a cool one. And then there's also been this new effort to kind of integrate that into PyTorch 2.0. So in PyTorch 2.0, there's this new torch.compile. And so this is similar, where you're just saying, okay, run torch.compile, it's going to try to compile the model. And then in theory, they've claimed a lot of benefits in terms of faster training, faster inference, faster everything. And so people have been kind of really happy with this, because you run this torch.compile step and you don't have to do any other work, and all of a sudden your model is massively faster. So people have been really happy with this. It's not in full PyTorch, I don't think, yet. It's just in the beta. So that's something I wanted to call out, because that's on the horizon. Eventually PyTorch will have that compile support directly built into it, and then you just run compile and you just supposedly have a fast model, about as fast as you can expect. So now we'll get to the parts that Jerry was asking about, like what is actually in that DL workbench from OpenVINO, and what are some of the other tricks that you might do. So one of the biggest ones, one of the easiest to do, is just reducing the precision. So most people for a long time have been training models in full precision. So this FP32 precision. And what has been found is you can actually train in lower precision and you still get great performance. And it actually makes your model about 2 times smaller. And you can do even faster and more operations, so you can fit more batches of data in. So there's various tricks to make that work stably, but it's kind of been abstracted away. So if you ever do half precision, like in HuggingFace, you just say FP16 equals true, and then you're good to go. You don't have to worry about it. It will train in FP16. And this is good because it makes your model potentially smaller. And also a lot of the hardware now is specifically designed for this. So a lot of the NVIDIA GPUs have tensor cores, and they can do inference on that specific data type even faster. So if you see some benchmarks and they're saying, wow, we're 16 times faster on some certain thing, it's typically mostly down to the tensor cores at this point. The GPUs themselves are not getting 16 times faster. They don't have 16 times more cores. They aren't running at a faster speed. It's now they have specific hardware. They have specific hardware on their chips that lets them do inference even faster for those specific things. So that's one piece of it, is reducing precision. So you can reduce precision at training time, and then you do everything in FP16, and then you do inference, and that's completely fine. You know that your training and inference is going to be the same. But then there's also the possibility of doing training at full precision and then inference later at half precision, because you just didn't prepare the model in such a way. So you can try doing that inference later and seeing what happens when I do half precision or even lower. You can go beyond that. And so you can see if the model continues to perform in terms of accuracy, and you can see how the actual speed changes as you reduce the precision. But that's something that you have to be careful of. So that process is called quantization. When you take the FP32 weights, you try to reduce it to FP16 or something lower. There's a lot of different techniques to try and do that and keep your accuracy. So one of the ones that's in OpenVINO is this accuracy aware quantization. And this is kind of interesting because one approach, the kind of naive approach, is just say, okay, lose half the precision and then see how it does. And that's okay, but it's not as good as this accuracy aware version where you give it some training data again and you run it through, and it will reduce the precision and kind of vary the weights just enough so you maintain your accuracy, because just that small imprecision across many, many layers can cause big differences. But if you line things up correctly in terms of how you do the various bits of rounding, you can keep exactly the same result. So in that DL workbench, you can do something where you say, give it the model, give it some training data, and then run this accuracy aware quantization, and then it will try to maintain as much accuracy as possible at this new lower precision. And so that's a pretty cool trick. I haven't actually run it myself, but it seems pretty cool on paper. And so lots of people doing stuff with FP16 and even Int 8 now, so even less precision. There's this guy, Tim Detmers, who's done a whole bunch of research on these language models and how far you can actually go in terms of reducing the precision and what tricks you need to do in order to get there without losing a whole bunch of accuracy. So if anyone is interested in going like even further in that extreme, you can look at this bits and bytes library, where a bunch of research has been done, and they've gone as low as 3 bits and said, how can we continue reducing the precision and getting more out of this? And they've done some interesting stuff in terms of seeing if they can fit massive models on smaller and smaller hardware by doing these sort of tricks. They have a table in here I want to show. Yeah. So this is them showing like, here's what you can fit if you do 16-bit, here's what you can fit if you do 8-bit. And you can see that you can fit even larger models when you start doing this reduced precision. And so that makes things more affordable for you if you don't have to buy a bigger instance just because you can't fit it into the memory of the system. Is reduced precision combined with batch normalization? I'm not totally certain on that one. I believe that it's precision all the way throughout. So I would assume that if you're doing FP16, you're also doing batch normalization on that data type as well. But I know that there has been work specifically on that. Like if you look at AMP or Apex or whatever it's called at this point, they do some specific trickery to make it work better. I don't know exactly what they're doing there though. I haven't dug in on that in too much detail. Yeah, thanks Ted for shouting out the paper specifically. Those links are all in the GitHub as well. And if you're interested, I don't have it available right now, but Tim Detmers on Twitter has some really cool posts as well talking about GPU hardware and which ones are the best price performance right now. So if you're interested in those, that's someone you should consider following. So the next thing after this is reducing precision, quantization, then there's also smarter padding. So something that we've kind of naively been doing this whole time is we have some max sequence length of our model. Typically it's like 512. Some models are even longer than that. You just take your input data and you say pad it to always be 512. So it just fits into your batches and slots in nicely to the model. But this is actually extremely inefficient because these language models, these transformers scale quadratically. So if you do 2 times as many tokens, you're actually doing 4 times as much work. And so if you could do anything to reduce the sequence length, you're saving yourself a whole bunch of compute that you no longer have to do. So extending this all the way to 512 is actually a huge waste. So one of the biggest speed up gains you can get is just reducing the sequence length. And so one simple way to do this, depending on your inference pattern, is just don't do padding at all. So if you're getting something where you're saying, we get one request at a time, you just don't do padding. You don't need it to be 512. You can make it be 25 or 30 or 50 or whatever the sequence length is that comes in. You just have to cut it off at the cap. It can't be longer than 512. But if you get something that's shorter text that passes in, then you don't have to do the full 512. And all of a sudden you're massively faster because the model has to do way less work. So that's one option. But then even if you have batches of data that you're passing in, you can still significantly beat just padding to 512, depending on your data. It always depends on your data. But if you have a batch of data, you can just pad it to be the longest. So instead of doing 512, let's say the longest in your batch was only 200. If you just pad the whole batch to be 200 instead of 512, you've just saved yourself a whole ton of compute by not needing to do that. And so that's one other trick that I've seen people do, is a sort of more dynamic padding even of their batches. So another trick that I wanted to mention is distillation. And so there's this trick of basically people have found that it's easiest to get a good model out of very heavily over parameterized models. So if you have something with 1 billion parameters, it's going to get a better accuracy than 100 million or something like that. But then it becomes this huge model that's difficult to do inference with. But what people have found is you train that massive model, and then you just train a smaller model to mimic that bigger model, and then you can actually get better performance out of that than training the little model on the data originally, because the bigger model did a better job at extracting out the information from the data. And then the labels that you get out of the model are actually denser than the labels of the labeling. Because if you have a teacher model, it's outputting probabilities for every single output. It's not just outputting a hard label. So if you have something and you're saying classify this page into 8 different things, your label in your training data is going to be something like 0000100 or something like that. But your output from your model is going to be actual continuous probabilities. So it's saying, I think it's 10% this, 20% this, 50% this, etc. And so that's actually giving a whole bunch more signal to your model. So there's a question, can you train the model with padding at 512 and then run inference at 200? Yes, you can. Yeah, so you aren't forced to always do inference at the max sequence length. And so HuggingFace will handle all of that for you in the model definition. You don't have to even really do anything different. You just say pass it an input of a different size, and then it won't have to do all of the extra work of 512. So that's a fairly easy thing you can plug in. So distillation is a really cool trick. You can, I mean, people have done these amazing things where you say, okay, take a 1 billion parameter model and condense it down to 100x smaller, and it only loses 2% accuracy or something ridiculous like that. So I've seen people have great success with that. And it's definitely a useful trick if you can fit a fit a smaller model that does similar things. That's kind of the ultimate winner, is you can do all of these things to do the computation faster, but if you can just do less computation, then it becomes a lot easier. Then it works on a bunch of different hardware better, and it doesn't take up as much space and all kinds of stuff like that. So the next thing that I wanted to talk about is sparse inference. So this whole time we've been kind of talking on reducing the precision. You can also just directly reduce the amount of weights. So people have found that a lot of these models, they just have dead weights that are basically doing nothing. And so people have figured out various different techniques to sparsify the models. So you have something that has 100 million weights, and then it turns out that a lot of those have no impact on accuracy at all. And so people have figured out that you can, with various techniques, reduce the number of weights. So you can just basically zero a whole bunch of them out. Some people have had cases where they can even say, okay, turn off 99% of the weights and you still get acceptable accuracy out of it. And so that's great that you can zero out a whole bunch of the weights, but typically with our inference with PyTorch or Onyx or whatever else by default, it's still going to do the same exact matrix multiplication or addition or whatever it's doing, because it's still operating on those matrices completely. So in order to actually get benefit out of this, you have to do sparse inference. So the sparse inference, you have to find some separate library. The one that I've seen is this neural magic one. And basically what it does is it will be able to do it instead of doing it dense where we were before, where you're saying run their matrix multiply on the whole matrix. Instead, it can do it and say, okay, there's only certain ones that are missing weights, so just skip the work entirely on those ones. And it's been optimized to do that specifically. And so people have found techniques to sparsify a whole bunch with losing minimal accuracy, and then you can take it to this sparse inference engine like neural magic, and then they claim all of these insanely cool things, like they're saying that they can do BERT inference 2 times faster on a 4-core CPU instead of a T4 GPU. So this is kind of incredible to say that you can do CPU way faster than you can do GPU. And this is relevant to the stuff that we're looking at because this is actually a BERT transformer model. So this is something that I've been interested in, but I haven't actually played with. I've seen a lot of their example code, but I haven't kind of integrated it with the stuff that I'm working on. But it seems very powerful. So if anyone ever tries it out and struggles through it or has success or whatever, I would be interested to hear how it goes, because on paper it's very good. And I linked this. There's a video from the founder, and he talks a whole bunch about it. So if you're interested in learning about that, that's a good video to watch. So seeing this CPU versus GPU comparison, I can talk a little bit about the work that I've done in the past. So like I mentioned before, I've done a whole bunch of stuff with OCR engines and trying to say, how do we do this as efficiently as possible in terms of cost efficiency, in terms of throughput, in terms of a bunch of different parameters, like how do we just make the best service possible? And so part of that is picking the hardware that you run on. So do you run it on CPU? Do you run it on GPU? Do you run it on TPU? Do you run it on this cloud or that cloud or wherever else? You have to figure out all of those parameters. So one of the things that I dug in on is AWS. They have their various different instance types. There's hundreds of them, and I kind of picked 2 different ones that I thought were kind of the best in terms of price to performance, and then I directly compared them. and it's kind of interesting. It always depends on your workload and what exactly you're doing. But for us, it made way more sense to actually use these T4 inference GPUs. And it seems to be common knowledge. Everyone talks about GPUs as if they're these super expensive things, and they're going to be 10 times more expensive than CPU instances. But that's actually not the case anymore with these T4 GPUs. So if you look at certain instances that are meant for training, they will be 10x more expensive. But these inference ones in specific are actually very good deals. So just kind of breaking this down, I looked at the C6i 2x large CPU instances. And what this is it's a 8-core system, 16 gigs of memory, and then it costs about 30 to 35 cents per hour. And so that's a pretty good deal relatively. You get a lot of compute for not that much money, actually. And it will cover most needs. You're probably not doing much bigger models than that, and that this can handle a decent amount of volume. But then on the other side, comparing against the GPUs, you get 4 cores, 4 CPU cores. So this is half of the CPU instance. You get the same amount of memory, and you also get a T4 GPU. And this T4 GPU has its own set of memory as well. So you're actually getting a bit more kind of total memory capacity there. And this ends up being like 50 cents an hour. So it's more expensive, but it's not hugely more expensive. And so I went and I said, I'm going to take this instance, I'm going to try and optimize it the best I can in terms of running OpenVINO, doing all of the stuff that I've discussed before, half precision, all of that stuff. Let's try to make that as fast as possible. And then let's take this instance and make it as fast as possible. And right off the bat, the G4DN with the GPU is obviously faster, like multiples faster than the C6i 2x large. So this is the one that we ended up going with because it gets us a GPU for so cheap. If you look at it, 50 cents per hour is just peanuts in relative terms. So this is what we ended up building off of. So if you're ever doing this, I highly recommend you go out there and then you look at the different instance options and you try and spec that out, and you understand like what is the trade-off, GPU, CPU, various instance options, what kind of performance per dollar can you get. So that's all I have for the notebook, but I did kind of want to mention one other thing I added into the presentation a little bit ago. So just kind of looking at the patterns of inference a little bit, I wanted to shout out one thing that I think is kind of interesting. So with online predictions, you kind of have this queue of work potentially, or you just have random work coming in. So you have a whole bunch of different people using your app or doing something else, and every time they click a certain button, it hits your model and then returns back a prediction. So this is kind of sequential or random, and it's just going in one at a time. That's sort of what the inference pattern might look like. You might have it queued, you might have it distributed, so it's going to a whole bunch of different workers. That can look very different, but in general, it's just random bits of work that are being sent to model or models on different places, and then a prediction is returned. This is in contrast to a batch prediction where it's like, okay, let's say that we have some database, it's a whole pile of data to predict against, and then we pass that all to the model. We probably batch this up in some regard. So if we have 100,000 rows of data, then maybe we actually send 16 over at a time or something, so we don't run out of memory on the model. But then at the end, we just have this big block of here's all of the inference that we've done. But then there's also sort of a hybrid approach to that, where you get some of the efficiencies of the batch stuff. So a big benefit from the batch stuff is if you're sending over 16 at a time, it can do it more efficiently than the online where you're passing it one by one by one, because the GPUs are good at this parallel processing stuff. So there's this kind of in between that can get you benefits of both. So this sort of hybrid approach is, let's say that we have some requests coming in, online predictions, and so they come in, you get a whole bunch of requests from your data, or from your customers or whoever's using your app or website or whatever else. And what you do is you accumulate a batch up until a certain batch size is met, or until a maximum latency. So you can basically sit there and wait until one of those conditions is met. So instead of just saying every time a new piece of work is given, send that directly to the model, you have something that kind of queues it for you. So you get some of the benefits of batch in that you're sending 16 bits of data instead of one all at a time, and then it can do all of the parallel processing at once. And so you might do something where you say, okay, if I have 16 bits of work in the queue, send it to the model. But you might have a scenario where you only have 3 bits of work and then the rest of the 16 never come. You can just say, wait, either until we get 16 bits of data or 500 milliseconds has passed or something like that, and then do the batch of data. And that can actually be much more efficient for you by sort of doing that queuing and batching for you. But then it also adds some complexity, because then you've done this batch and then you have to split it back out at the end. So you gave it your batch of 16, and then you have to break it out and send the individual responses back to all of the people at the end. So yeah, that's everything I have for today. I would have liked to touch a bit more on some of the API stuff, but I think that was going to be too much for today. I saw there was some discussion going by that I wasn't keeping up with. Do we have any questions or anything else we'd like to discuss?
I think a bunch of that might have been me adding random comments, so you don't have to worry about those. Any questions for Ryan?
Have you tried, have you seen any difference in training, or I should say model performance by increasing data set size? Like at least like 3 times, like very significantly, not by like a little margin. I mean, like tripling your data set size.
In general, more data will get you more performance, but it doesn't necessarily completely change your I mean, it depends on the initial size of your data. So if you have 1 million samples to start with, going to 3 million might not change a whole lot. But if you have 100 and you go to 300, then that's probably going to help you a whole lot more. It just depends.
Yeah, there's a lot of research that kind of talks about power law curves. So, the benefit, like Ryan's saying, when you're small, you're getting better, but you're now just squeezing out drops when you're already at 1 million.
And all those analyses assume that the data is obtained the same way. So, and that they're part of the same distribution, random distribution. If there's anything at all different about the new data, then it will have a massive change to your accuracy.
What sort of model size are people being able to shrink these things down to?
I mean, it really depends. So like one of the most famous ones is distobert. And so people have taken BERT that was originally 110 or 130 million parameters, and then they can get it under 10 million. So they can go
Hmm.
10x smaller, and it
10x
actually
smaller.
is similar performance. It's not exactly the same, but it's like if you're saying I can get it 10x smaller and it's only 1% accuracy difference, that's actually
Sure.
very, very good.
Sure.
But it really depends on the model. I'm actually kind of curious, like we have all of these scaling laws of like, how do we go to 175 billion parameters? What
Right.
happens if you distill that? Is it possible to fit that in a 1 billion parameter model? Can you do that same 10x, 100x or something, or can you go even further? I don't know that that's well studied yet, but I mean,
Okay.
it's very interesting. Yeah.
Yeah, I know in the I play in the tiny, machine learning space. So, when you're talking about a machine with 64K of real RAM on it, you have some real constraints, and you don't see much in the model of voice type recognition or even sentence recognition. But you do see a lot of image models being shrunk down that far, doing very, very well. So I just wondered how far they had taken kind of the language models down to a small space. Thanks.
Have you read the Tiny ML book?
Mhm,
There's
mhm.
one from O'Reilly. I looked at that a while ago. I didn't get particularly far in it, but I believe that one of their first examples was actually a
Well, they
voice
do a
recognition type
wake
model.
word type thing,
Yeah.
but it's binary, right? It's like yes,
Yeah.
no type thing, not a sentence,
Yeah.
coming
Yeah.
in. Yeah, because I know Pete and Daniel a bit, so they're the authors there, and yeah, that
Mhm.
it was very small because that's like 2018, so way
Mhm.
back in the old days type stuff.
Mhm.
So yeah, they both have their own separate companies now, I guess. So yeah,
Yeah.
okay.
Yeah. I think that area is super interesting. I tried to get into it, but I just haven't been able to spend enough time on it. I mean, it's incredible that we operate at like such different ends of the spectrum, where it's
Right.
like, how do you even fit a model in that footprint? It doesn't even make sense to me because I'm
Well,
used to all of this huge stuff.
yeah, just go to the Edge Impulse site. They have tools that make it pretty easy for you to do that.
Mhm.
So they have some neat stuff. So anyway,
Hey, Ryan,
Yeah.
I don't really have like a a smart, eloquent thing to say, but I thought that maybe one thing you could touch on is just like some pitfalls around like data prep, and the fact that like you better make sure that however you prepare your training data, that your inference pipeline like kind of has the same stuff. Like I get thoroughly confused. Like, am I supposed to like scale my images or not? I don't know.
Yeah. I would,
What
yeah,
kind of tool do you use for data prep? Like libraries as well.
It's whoops. It doesn't even have to be anything fancy. It's just like if you center and scale your image values. So like, if your training images are like just sort of whatever, and then like you're actually doing inference on your phone and all the images are really dark, then like that might not work so great. You might need to brighten them up a little. Like there's pretty basic things, but I don't know. I'll let you try and speak to it.
I mean, that's a huge thing that I've run into where, I mean, anyone who's done a Kaggle competition has done the thing where they go, "Oh, I had this great model," and then they put it up on Kaggle, and then they get punched in the face when they realize that it gets 0.00% accuracy because they did not set up their inference correctly, and they didn't normalize their image, or they didn't do something else. You have to be very careful that you're matching your training and your inference, and that the input is from similar distribution, and you've got all of that stuff lined up. Even in my work now, I've been trying out different OCR models and different stuff like that. So I've tried out some paddle work. I tried out some research work called Parsec. And so I was trying that stuff out, and it's very, you would think that it would be like the crucial bit is like, how do I do inference with this? but it's very unclear sometimes because they have their training code, they have their benchmark saying I got this accuracy, but then if you say I want to do inference, what do I actually do to get to that point? A lot of people will have a different process of opening it in pill or opening it in CV2 or opening it with some other function. And is it supposed to be int 8, floating point 32? Is it supposed to be divided by 255? And so I very often am just reaching in the dark saying, okay, it got 0% accuracy. Okay, try dividing it by 255. Okay, got 75% accuracy, but that's still not quite right. So like something else is going wrong with the normalization. So I will say, to your point, Ted, that's like, you really have to make sure that you're getting that right. One of the things that's interesting in OpenVINO with some of the vision stuff is you can shove that normalization step inside of your model. So it's just directly an option saying, do you want normalization? What is the expected input format? Is it going to be RGB? Is it going to be BGR? Is it going to be something else? So that was something I found kind of interesting in the DL workbench, is like, you can just say like shove more and more of that pre-processing stuff inside of the model so you don't have to worry about any of it, which I thought was cool. And they were also saying that it can make things faster by having that part of the graph rather than part of your external code. So that stuff is very, very important. With the transformers stuff, we're kind of lucky with the HuggingFace stuff because you basically say auto tokenizer, load in the tokenizer that I have and just run, and it will hopefully match whatever you've got set up and you won't have any problems. But I've even had problems with that where you end up with something that ends up out of index, you have a new word that's never been seen before, or you have something else that goes awry, you load the wrong tokenizer for the wrong model or something like that, and then all of a sudden you just get 0% accuracy out of it. So there's, I mean, you really have to be careful with that inference pipeline and make sure you're doing the same thing. Very, very important step.
Thank you.
What would you use the library? Would you recommend learning pandas? Because I'm just starting out, kind of, I'm diving deep in this.
It depends on the data. So pandas is good if you have some sort of tabular data, but if you have images, then you maybe need something else. It just depends. There's a lot of different tools out of there. There's not one that will handle everything. There's another question in the chat. What do you prefer for implementing batch processing? Any feedback on, is it prefect? If that's some tool, I'm not aware of it. If you mean prefetch, I'm not sure about that either. So I haven't done a whole great deal of work with that. There's a bunch of different tools for handling that. So like NVIDIA has their own Triton inference engine, and there's various different tools inside of Google and Azure Cloud and whatever else, and load balancers, and there's all kinds of stuff that I haven't specifically worked with. So I don't have any specific feedback on that. But yeah, I know there's a lot of tooling related to that. At H2O, we have a MLOps tool that handles a lot of that stuff, but that's not my area of expertise necessarily. All right, if no more questions, we can wrap it up there.